So as we are to consider our DC machines in general, considering the DC generator, is it a DC motor? We are going to see that there is a need for us to be calculating or determining their efficiency. Why is that? Because as you consider, the efficiency is the ratio of power output. It's actually output to the input. So as we consider that efficiency, when it is calculated as a percentage, we need what is on the output to what is on the input. The DC machines tells us that efficiency can be calculated. Why? Because on DC machines, whether you are to consider any machine that you are given, there is the input power that is being given. There is also the output. So by just having these, efficiency can be determined. Meaning to say, as we are to consider the efficiency as a percentage multiplied by 100% of any machine. From this concept, we can now say the percentage efficiency can be taken from the output power. Output power over what? Input power. So it must be input power times 100%. As a percentage, you must multiply by 100%, which you can just write in short, P out over P in times 100%. Percentage efficiency. If it is a per unit efficiency, because it can be like that, where you calculate what is referred as per unit efficiency, which is not that much important in us. We're going to see that as we move on in our N5, N4 there. Per unit efficiency is just a value where you divide the percentage by 100. If you remove this here by 100, if you divide by 100, you have per unit efficiency. So it's just P out over P in. So in order for you to obtain the per unit efficiency, you simply take your percentage efficiency that you calculated, divide it by what? By 100, just like that. What you had as your percentage efficiency divided by 100, you have per unit, not percentage. So as we are to consider this, let's say you are given, let's say you are given that this is the input, this is the output. Guys, you can calculate your efficiency. But now, as with our DC machines, we must consider also the issue of the losses as we have them. From the input, during the process of converting, now remember you're converting the power, one form of energy to another. There is conversion which is taking place. Considering that you are to deal with a generator, where the input, there is what? Where the input is mechanical and the output is mechanical, is electrical. That conversion alone, you're dealing with a motor where you have the input as electrical and the output as mechanical. When it is being done, the conversion, there are losses which are bound to occur. So these losses that are bound to occur can best be described as with the type of machine. They are best to describe that. So as we are to consider, as with the type of machine, let's take what we had when we talked about these DC machines separately. Remember when you had a generator, if you to consider, let's just take even a series. When you had a series, I just want you to see so that you can have a proper understanding. When you had a generator, this was your supply, remember? Sorry, this is a generator. So you're going to have this supplying the current, and this you were having output because the current is being supplied there. So you're going to have the power output. And here you're having what? Your input power, which I said is the mechanical. This is what we had. So considering that alone, to say we have a generator, guys, considering that alone to have we to say we have a generator, we can see that it is something like this. On our generator, the input as we have it, okay, the input, the power that is entering, which is your mechanical output, which is what? Which is our electrical now, which is our power output, which is taken from the voltage and current. Remember, at the output there, your power was voltage times. Remember those calculations? I'm just giving you a basic one. Your power is going to be calculated voltage times current because it's electrical power. It's electrical power. So the input, because this power that we are having at the input is mechanical, there are a lot of things that we need there in order for us to have that calculations depending with the arrangement. So because of that difficulty, because of being mechanical power in its calculation, we can have it in terms of the output and the losses. Remember when the input was there, it is originally as it is. But because of the losses that are happening, there are losses there that happened in order for you to obtain this output here. There are losses. So as you see the output, it's not going to be input. It was supposed to be like this. That was supposed, if there are no losses, if there is no loss at all, it was supposed to be like this. The input was supposed to be equal to the output. But because we lost these losses, we are supposed to add the losses that we lost in order to get back the input power that we had. We must add those losses to get back to the input power that we had. So this is for any machine. This one is now for any machine. For any machine that can be related. For any machine. Meaning to say from the same formula you can make the subject P out. Take the losses this side. So we are going to have P out is equal to what? If we take the losses this side, it is going to be P in minus the losses. If you want to make the losses the subject, we can also do that. In this case, you have to take P out to the other side. So it's going to be P in minus P out. From this. So this is what I'm trying to say. If you are given, let's say you're considering a generator like this. You have your input on the output, and you're supposed to have this as efficiency. Let's talk of efficiency, percentage efficiency. Remember, output over input times 100%. The output being electrical and something that can be calculated, meaning to say we can write our answer in terms of the output because this can be calculated. But look, the mechanical, there must be a method of calculating that. So it means that part that is difficult for us to calculate, let us write it in terms of P out. Is there a formula where P in is written in terms of P out? Yes. P in terms of P out, it is equal to what? This is what we have. P in. Because that part, guys, we cannot calculate, like for us to calculate, we must have a specific formula there. But we do not have for now. So we're going to write it in terms of what we can calculate P out. P out can be calculated. So in place of that, P in can be written that way. So you're going to have P out as P in, which is same as what? Output power plus the losses times 100%. But remembering that the output power can be calculated if we are given the voltage and current. In place of that output power, we can use what? Voltage and the load current. So the same formula can be given as, if you consider the voltage times the load current over what? The same output power, voltage times the load current plus the losses. The losses for now, we are talking about all the losses combined, everything that has been lost. There is going to be another part where we are going to be talking about differently. These losses taken differently to say we have got this type of, and this type, and this type. But there we are combining all of them, all the losses that can occur. For a generator, we can end up with these formulas. For the percentage what? For the percentage efficiency, considering that we are on a generator. With this understanding, if it was a motor, these formulas here that we are seeing, like I say, these ones for input, this relationship here is for any machine. Any machine, it does not say it's a generator. A generator, it has losses. A motor, it also, in terms of the power, this is for any machine. It can be for a generator. It can be for a motor. But now when you have to consider to say a motor on its own, because there we are considering a generator, you want to see what will be the efficiency on a motor now. The efficiency is not going to change as with the calculations to say the efficiency, which is our percentage efficiency, is equivalent to the output over the input times 100%. That part is not going to change. But as we saw that one of these powers, depending with this, if one of these powers is to be mechanical, the challenge is where it is, because the power of the electrical can be calculated. So the question is, as we are to deal with a motor now, which of these powers is electrical? Remember, a motor, the conversion is from electrical to mechanical. The input is the electrical one. This one. It is the electrical one. This one is the one which is our mechanical one, which is at the output. That is where we have that is why even if you consider a series motor, just a basic view of what you're having. Remember, you're having what? Current being drawn. And we're saying this is where we have what? Our output. I mean, this is where we have our input from the load that is being taken. We're going to take this as the input. You're now on a motor. Remember, we're now having on a motor with a voltage there to the output, which is the mechanical. So if you consider this, guys, from a motor, you see that, okay, so since power is entering, it's entering what? A motor. It is entering input. Then what is it that we have there? We are now having output. Input is what? Electrical voltage times current. It can be calculated. This time, input can be calculated because it's what? Electrical. The output is the one now that has a challenge. So that's where we have to write the output, just like what we had here. The input was difficult for us to calculate when it was a generator. So we had to write it in terms of what? The losses. So in terms of the input here, we'll be just saying, all right, so P in terms of this one that can be calculated is P out plus what? Plus the losses. Where P out is what? Voltage times current. So we have something that can be calculated now. Since also here if you're dealing with a motor, the input is the one that we have now this time. The output is the one that is difficult because it's what? It's mechanical. So we have to write it in terms of what we can calculate. So how do we, is there a formula that can relate output to input? Yes. Output is equal to what in terms of the input for any machine. For any machine, the output is going to be given as what? As P in minus the losses. Why writing it? Because P in can be calculated. We saw that P in can be calculated from what? Voltage times current. Then we subtract all the losses. So with this, efficiency of a DC motor can be calculated. So considering that you are calculating the percentage, all right, just for the specific part here. So the efficiency has to be calculated. So let us just also here, maybe, right? But you can even just add this so that you do not have, you can just add a generator just for you to be, right? For you not to have a confusion, guys. Now you're on a motor. So I'm just gonna write a motor in short there, but do not worry about this. As long you're calculating what? Your efficiency. Output over input does not change times 100%. But we saw that the output can be written in terms of what? In terms of the input power. So it can be given as Pn minus losses over Pn times what? 100%. That is what we're going to have there. And we saw that the input power that we are talking about here can be calculated from voltage times current. So in place of Pin, we can simply write voltage times what? Load current minus the losses over what? Pin, remember? That's your voltage times what? Voltage times current. So this being multiplied by 100%. It's going to be your percentage efficiency of what? Of the motor. So just depending with the textbook, sometimes they will just divide by VI here because remember this concept that if you're given A plus or minus B over A like this, you can divide to say it's A over A plus or minus B over A. So the A and A are going to cancel, then you get 1 plus or minus B over A. So this mathematical view, you can see that these two are the same. So you can just, okay, let me just divide that times what? Times the current here, which is the same, minus the losses. We have to divide again by the same voltage and current. So these two cancel. You get 1 minus these losses over what? Over voltage times what? Times current. They can present it that way. Guys, it's them. They can present the way that they want. You also can present your formula in the way that you want. So you can just leave it like that. Efficiency of a motor. A DC motor can be calculated. So this is what we're going to actually use in our calculations in the examples that I'm going to be showing you. But as we are going to have this for the revision part, I want you to go through the losses, just that you understand all the types that you are going to have of the losses, because they can be a condition where they just need you to understand the types. We've got two major types that we have, which are the constant and the variable losses. Talking of the constant losses, so we have got the part of the constant losses, which is where we can consider the shunt field winding losses. This part is which carries the shunt field winding losses. Okay, and the shunt. Remember, when you're talking about the shunt, along the shunt, we need the power there along the shunt field, the shunt, guys. We're talking about the shunt. So they can refer current voltage across the shunt. Like this is just like the field, but it's the shunt like that. So what is the relationship? It's power. Losses, this is power. When I talk about losses, this is power. So ask yourself, if I'm given current and resistance, how can I calculate what power? How can I calculate power given current and resistance? Remember, power is I squared R. So it's the current of the field, which is the shunt, times what? The voltage, the resistance, which is the resistance in that shunt field. So they can give you this as RF, as IF and RF. They're just saying the resistance of the shunt field. The resistance of the field. It's what? The shunt field that we're talking about. Also along the shunt, remember, if you're dealing with the shunt motor, guys, it can be a generator. What if you're dealing with a shunt? Remember, I talked about this issue of the terminal voltage. We saw that the terminal voltage is the same voltage that you used when you're calculating the current across the shunt. We're using the terminal voltage. We need to say voltage at the supply is the voltage that is across what? Is across the shunt. So meaning to say there is voltage, there is resistance, there is voltage, there is current. Can we calculate power from there? Yes. Voltage times what? Voltage times current. We can use that as long as it is power that you are calculating there. So from this, you can also use voltage times what? Voltage times current, where the voltage is the terminal voltage and the current is the current that is on the shunt field, which we can just write as IF. So like I say, these part that we have, they can write it as what? IF squared RF. Okay, or voltage times what? IF, like they're writing the field. It's the shunt field. It's the shunt field that we're talking about there. All right. So this is part of your constant losses. Talk of the ion friction. These are also to be considered. We also have the part of the ion friction. All right. So we said ion, then friction and windage losses. Don't know how do you pronounce this one, windage or windage losses. Yeah, to be carried as one. To be taken as one. So these ones we are going to see later on as we are to deal with our calculations. They can use the letter C to represent these losses. They can represent anything for that part of the losses. We're going to have an extended explanation in our next classes when we are to deal with these losses. But here we just like to know these which losses that we have. Then we also have the variable losses. Under the variable losses, that is where you are referring losses such as armature winding copper losses. All right, where we've got the armature winding, that's the armature winding copper losses. Copper losses also to be taken. This is part of the armature. So you must have armature current and resistance. Remember, current squared times resistance, and it's part of the armature. We have part of the series field. Series field is also to be considered. Winding, the series field winding, copper loss. We are in the series. And in the series, remember when you're dealing with a series combination, what is it that we know about the currents in a series? The current in the series is the same as the armature current, is the same as the load current. So given resistance and current, I'm just going to use current squared times resistance, but is the current is the same. Remember that part of the series, guys. So meaning to say we are going to have current squared, I squared times what? RSE, where we are talking about what? The current being the same. Remember that armature current is equal to the series, is equal to the load current when you're dealing with what? A series. They're just referring you back to what you had before, guys. Power there. How do you calculate power if you're given current and resistance? We have the interpole. Interpole. So we have also that part of the interpole winding copper loss. Interpole winding copper loss. These are also to be considered. This is where also the armature current is flowing. But the resistance, now you have to consider the resistance of what? The interpole. So the resistance of the interpole, just going to write Ri like this for interpole. But what we have there is what? Power. So it's going to be a squared. Remember power, I squared R. So we can see that power. It's just like, what is the current in that armature? What is the current in that series field? What is the current in that interpole? It's armature current. They're all part of the what? Armature circuit. Talk of the brush contact. Okay, the brush contact resistant losses, they can give you this, the brush contact resistance losses. So we need this because in the next classes that you're going to be having, they'll be expecting you that these formulas, you know them. So it will be just a continuation. So they were talking of the brush. So armature squared, armature current squared times the resistance of what? Of the brush. Same, we can have armature copper loss. When you're dealing with the armature winding, direct where the armature is, we just use armature current and armature resistance. But when you're just saying the exact part where the armature, like just considering armature copper loss, where now we are considering to say in this armature circuit that we are having, because we'll see that it can be combined to give us one, because inside the armature, where the armature current is flowing, we have armature current here, which is flowing in the part where the armature is, exactly where the armature is. The armature current, which is flowing in the series, the armature current in the interpole, the armature current, which is also part of the brush contact. All these resistors, they are affected by the armature. Remember when I talked about the resistance of the armature circuit, this is where the armature current is flowing as it is. So instead, we can see that this formula can be written as armature current squared times the resistance of the armature circuit as the armature copper loss together, combined, where we can simply see that we are simply adding, like if it is armature current, the resistance of the armature circuit, we add all the resistance that are there, the resistance of the armature part as it is the armature winding, the resistance of the series, the resistance of the interpole, the resistance of the brush. They are now taken together, combined. Resistance of the armature circuit, where the armature current is passing as it is, as it is armature current as it is like this. It is affecting direct. Those resistors can be combined to a single unit, which is the resistance of the armature circuit. So please do revise as much as you can, go through your other losses, ion losses, the eddy current losses, the hysteresis losses, mechanical losses as they are presented in different ways. And these losses, like I said, we are going to have them in the next classes where we actually need to apply. But for now, from this information that we just had on just calculating the efficiency, with these losses being combined, we want to see how questions can be given. We are not considering to say there's there's this type of loss here. No, we are just considering all the losses combined together. How questions can be given if these losses were combined. All of them. We saw that on a motor, we are going to have efficiency being calculated from this formula. Not forgetting, on your generator, we also listed the formulas that are necessary in order for us to calculate that efficiency. So let us just check one or two questions which can be important in our calculations. There we are given the first part here. Calculate the input power. Calculate what? The input power of a 50, techno, they are saying of a 50 kilowatt DC machine. Did they specify which type of power is that? No. They just said of a. So under an exam condition, if you're given the power that is given, the given power is the output, unless they are going to state otherwise. The given power is supposed to be what? Output. So take note under an exam or under question answering. Under question answering. Okay. The given power. The given power is your output power, unless stated otherwise. Unless they can give you something to say, okay, this is input. When it is like that. When you guys, but even telling, like, if you're given to say calculate input, which other power is there? Which other power is it? That will be output. So that's another way that you can actually get rid of this question. So they are saying you are supposed to calculate the input power when the power is given as the output of 50 kilowatt DC machine. We do not even want to know whether it's a motor or it's a generator. It's just a DC machine at an efficiency of, when this type of a question is given, when this type of a question is given, when this type of a question is given, they just want you to know what is efficiency. Because efficiency, whether it's a generator, whether it is from a motor, is the output over the input. Output over input. We're not even worried about the losses or what now. So if we divide by 100, what are you obtaining? Per unit what? Per unit efficiency. Divide by 100, that will be 0.9. So remember that per unit efficiency, when you divide by 100, it's simply P out over P in. There's no need for you to multiply by 100. So use the decimal. 0.9 is equal to what? Output. This is 50 kilowatts, the power that we are given there. So we are given power 50 kilowatts. Already it's in kilowatt. Over what? The input, we do not know that. So you want to calculate the input power, right? So you're going to cross multiply so that we can solve this equation. So that is going to be what? 0.9 times the input power, 1 times 50. We are going to obtain 50, which is already in what? In kilowatts, remember? So the moment you just divide by 0.9 by 0.9, it means the power that you are obtaining there is already in what? Is already in kilowatts. So take note there. It's already in kilowatts. So it was going to be 55,556 like this, which is in kilowatts. So there they just want you to use the basic formula of your efficiency. Example 5.2. A 7.5 kilowatt DC motor. There they are specified. It's a DC motor. And they told us it's a 7.5. Like I said, moment you are given A, that's your output power. 7.5 kilowatts. Draws 35 amps from what? We are given the current which is being drawn from the supply, the load current of 36 amperes from a 250 volt supply. Calculate the efficiency of the motor. That is where it is important to know you are dealing with what this time? The motor. Because the effect is on how the powers are being presented there. Okay, no problem. We saw that. That is it. A, we need the efficiency. So as a percentage, the formula is not going to change, no? Formula is not going to change. Percentage efficiency. It's power output over power input times 100%. And it's a motor, as we saw that. On a motor, the output is the mechanical. So it is difficult for us to have this. That is why they gave you the. Because you're supposed to calculate it if it was not given, but they gave you. The input is what? The input is electrical, remember. So if it is electrical, it's an advantage because we are given that one which is difficult for us to calculate. And the electrical, we know that it can be calculated from voltage and current. Remember, from electrical, Pn, voltage times what? Current. So it can be calculated. We have the voltage. From the supply, the current is also given 36 amperes. So we're going to calculate the power, input power, and that was going to give us 9,000 watts. Since this is already given in kilowatts, let's convert also this to kilowatts, divide by 1,000. So that is going to be 9 kilowatts as our input. It can be calculated. The input is an advantage because it's a motor. We can calculate that. So the percentage efficiency now can be calculated because we have it. Output is there, 7,5. It's kilo over what? P in, it's also in kilo. So just leave that. It's like kilowatt over kilowatt, guys. It was going to cancel. So just leave that part of kilo. As long the units are the same, just divide the numbers as they are times 100%. You are going to obtain what? The efficiency. And that was going to give us 83,333 and so on percent as your efficiency. B, the total losses occurring in the motor. Just knowing input and output. Remember the input, it entered as this. Due to losses, this is what came out. So what are the losses? We can calculate the losses from there. Remember from our formulas, I said for any machine, losses can be calculated from the input. It's Pn minus P out. We saw this from our formulas. If you have to consider here for any machine. I don't know which formula I used to. Is it this one? You make losses the subject. Are you used to this? You make losses. Whatever formula that you are used to. But at the end, losses can be manipulated to give us P in minus P out. Where we have the input power, 9 kilowatt in kilowatts. The output also in kilowatt will give us the losses in kilowatt also. Remember, losses is power. So it will be 1,5 kilowatt. These are the total losses which were incurred. These were the total losses that were incurred. These are the questions, guys. Another question, considering that this time they are saying a DC series generator. Why telling us that it's a series? Why are they telling us that it's a series? There is something that we need also about the series. There. They are saying it's a series. It's a DC generator. Remember, a generator is going to be supplying. This one is a generator, not a motor. So it's going to be supplying the current. Okay. So according to the information they are saying, delivers 15 kilowatt. It delivers, meaning to say at the output. Because remember, this is your input this time, generator. So at the output, it delivers. We are given the output power. From this, output power is given. It delivers 15 kilowatt at a terminal voltage of what? Of 300 volts. At the terminals there, where the output power is, there's also a voltage of 300 volts. If the generator is functioning at 86% efficiency, the percentage efficiency is given as 86, which you can just write as per unit efficiency, just divide by 100, which is 0.86. Calculate A, the power input to the generator. Calculate the power input to the generator. All right. With this information that we have, we do understand the input to the generator is the one that we are considering there. as the mechanical. So if there was a formula, we're just going to use the formula, but with this information that we have, the formula will be limited. So the only way for us to have the input power, it is either we are given the losses and it must be taken from the losses. It can be taken from there, or it can be taken from the efficiency. If you check, they want you to calculate the total losses occurring in the machine later on. So meaning to say the part where the losses is not going to work. Remember, there's a formula here which consists of the losses. P in, it's P out plus losses. It's not going to work. So we have to think along now. The efficiency, we are now bound back to the efficiency. And we have that efficiency we are given. So from efficiency, we saw that efficiency, it's P out over P in. If it is per unit efficiency, because we divide it by what? 100%. So the question is, are we having P out? No. Okay, they say deliver, so you're given. So it's an advantage. If you're not given, you're going to use the current now, but there you're already given. So the P out is there. The efficiency is there. So P in can be calculated. We're just going to cross multiply. So if you cross multiply there, it's going to pay per unit F times P in. Then you divide with what? Per unit efficiency. That was going to be the case. So if I'm given efficiency, guys, so our power, 15 kilowatt, as it is in kilowatt, it's a kilo there. Kilowatt divided by per unit efficiency, 0.86. So you're going to obtain the input power in kilowatts. So that's the idea there. So 15 divided by 0.86 was going to give us 17.442. That's 442 in what? In kilowatts, as I mentioned before. B, they need you to calculate the armature current. Being told it's a series where we can see the armature current, the series field, whatever that you have. We do understand that it is the same. It's a series circuit that you're. Let's go back to our series circuit, guys, as we talked about. Series wound. And it is series wound. We saw that the armature current is the same as the series field current, is the same as the load current. So can we calculate the armature current direct? We do not have the generated EMF, so it was going to be difficult for us. We are not even given these resistances of the armature, resistance of the series field. So we can use any one of these as long it is possible for us to calculate it. Why thinking of the load current? Because at the output, which is electrical power, we saw that it's voltage times the load current. And with that, we can calculate the value of what? The load current divided by the voltage. So meaning to say the load current was going to be obtained from the output power. Remember output, guys? You are given that. It was 15 kilowatt. 15 times 10 to the exponent of 3. This is not power that you are calculating, so use the values as they are over the voltage. Remember, our terminal voltage is 300 volts. So with this, you're going to obtain the load current. You're from the formula, you're obtaining the load current. But this is the same because it's a series circuit. They could even ask you to calculate the series current, series field current. It's the same. It is a series, so it's the same as the armature current. So therefore, our armature current is 50 amps also. Just like that. That is what they wanted. Then the total losses occurring in the machine, as long as it's a DC machine, as long as you're dealing with a machine, how do you calculate your losses? We saw that losses can be taken from the input minus the output, because the input entered and it occurred losses to give us this output. So the difference are the losses. So the input power in kilowatt, 17,442, minus the output power also in kilowatt. So it was 15 kilowatt. We're given that output power. Remember, 15 kilowatt here from here. Output power was given as 15 kilowatt. Delivers at, which is delivered at. The difference there, 2,442 kilowatt, are the losses that were being encountered. So there we are talking about losses just like randomly taken. Say we are not even specifying which type of loss is this one. There are going to be methods, tests to be made in calculating of efficiency differently. So that will be our next classes, where we are going to be talking of different methods that are used now in determining of the efficiency. But on a basic calculation of efficiency, this is what you just need: output over input, and knowing the relationship which occurs for any machine between these powers, for any machine that you can talk about. Yes, you have to go back and consider to say, when it is a motor, what type of power is input? What type of power is output? How do you know that? From its conversion of power. From its conversion, how was a motor converting power? How is the generator converting the power? A generator, mechanical to electrical. A motor, electrical to mechanical. Understanding that, you can answer as many questions as you can. So that's what we had, guys. Till we meet again.